Hello, everyone. My name is John Makhoul, and I will be talking to you about what led to the modern era of benchmarking in human language technology. Now, there has always been a desire to benchmark our various technologies, but it took the convergence of a special set of circumstances to light the spark that ignited the practice of benchmarking on a consistent and enduring basis. Because that spark was lit by two competing paradigms in automatic speech recognition, in this talk I will retrace the early history in speech recognition as I witnessed it from over 50 years ago to 1987 when that spark was lit. I have entitled my talk The Dawn of Benchmarking. 1987 was a watershed year in the history of benchmarking in human language technology. First, it was in automatic speech recognition, which is the subject of my talk today. Now, there was always a desire to benchmark, but benchmarking took off with the confluence of several factors. First, the insistence on benchmarking by the funding agencies and the development of common corpora and defined metrics. These are the necessary conditions for benchmarking. But I will argue that it was the use of trainable systems which really lit that spark and that caused the wide participation. With this wide participation, which resulted in the acceleration in the technology development, and that positive feedback loop uh, created the beginning, basically, of convincing people that benchmarking is really important. This is a schematic of the different generations of automatic speech recognition. 60s, 70s, early 80s, etc., 2G, 3G, 4G. Um, the, the most dominant method in the early years was what you would call heuristic approaches or knowledge based or rule based. And that was the dominant paradigm in speech recognition for many years. I will say some more about that a bit later. In 1968, Vinsyuk in the Ukraine was the first to use dynamic time warping for pattern matching of words. And then in Japan, they picked that up, and then AT&T in the US. But these were considered like engineering approaches, and frankly, they were looked down upon by the speech scientists, and they thought, well, it was not science; it was just engineering. And also by 1980, when hidden Markov models started gaining steam, there was no need for dynamic time warping, any longer. So the main two approaches really were the knowledge-based heuristic approach and HMMs. So I will talk about both of these. The heuristic approaches, these were historical in nature, inspired by speech production theory and perception experiments. The main spectrogram, the main tool was the spectrogram, and that tool became even more important when people discovered that the basilar membrane in the ear acted as a filter bank. So basically, the ear was doing some kind of a spectrogram. So, and seeing the spectrogram was amazing, and it was very convincing that really this is a tool of choice. And learning to read spectrograms was fun and seductive. If you have tried it, if you have not tried it, I would suggest it. It's very nice. The problem is making that as the basis for making rules for how speech is done. And the speech scientists had hypothesized distinctive features, phonetic distinctive features For example, high, low, and front, back for vowels. And people wanted to find invariant acoustic correlates to these distinctive features. And the high point of trying to do this, it was the 1983 symposium that was held at MIT in honor of Ken Stevens' 60th birthday. The title of the workshop was Invariance and Variability of Speech Processes, which was the proceedings were published in 1986 by Perkel and Klatt. And the main notion was if you could just find those invariant acoustic features, the problem would be solved. In that workshop, Rich Schwartz and I gave what you would say is a tongue in cheek commentary saying, look, we don't know this knowledge that we're talking about, we don't know what it is. We don't know what these invariant acoustic features are. So we're going to model our ignorance, and we're going to do that using statistical models. Now, I would like to highlight two reactions to difficulty of doing speech recognition. One from AT&T Bell Labs, John Pierce, and another is a study that ARPA commissioned in 1970. John Pierce published a letter in the Journal of the Acoustical Society of America in 1969. He entitled it Whither Speech Recognition. And it was a scathing diatribe against people working in speech recognition. He called them all kinds of names. You should read that article. But what one sentence that attracted my attention was that performance will continue to be limited unless the recognizing device can understand what is being said with something of the facility of a native speaker. And he reasoned that since we don't know how to do that, we don't know how to do something to do the understanding part like a human being, Pierce decided that speech recognition was hopeless, and he stopped all work in ASR at AT&T Bell Labs. Now that work was not continued until John Pierce left AT&T. He retired, and Jim Flanagan took over, and then he continued the work in speech recognition. At around the same time, ARPA, to say something about what's going on at ARPA. ARPA is the Advanced Research Projects Agency. Now it's called DARPA. Anyway, at about the same time, ARPA funded the building of the ARPANET, which was built by BBN and was first demonstrated in 1969. This was, of course, the precursor to the internet and the introduction of email around 1971 with the @ sign. Again, Ray Tomlinson at BBN did that. And people did not have email until the 1990s, but the ARPA contractors had email since the early 70s. Now, also, ARPA said they were interested in using the ARPANET to transmit voice. Now that we can transmit data, why not transmit voice? So they established a program of network speech compression, and that lasted from 1972 to 1982. I participated in that program, and the experiments that were done laid the groundwork for the development of the voice over IP protocol, which now is in wide usage with applications like WhatsApp. At the same time, around 1970, ARPA had the desire to use human language, especially voice, to communicate with computers, to really communicate with computers using voice. So they commissioned a study in 1970, ARPA study, and so they addressed the issue of what was standing in the way of advances in speech recognition. The committee had people in it from artificial intelligence, NLP, and speech. It was chaired by Alan Newell of AI fame. The report was published in 1971, called Speech Understanding Systems, Final Report of a Study Group. Now, the assertion that was made in that study was not a conclusion, it was an assertion that a speech recognition system will have to employ information from all levels, from the acoustic to the semantic, to effect recognition. Now, it was a good study, and the first conclusion of the study was we need to use understanding to help the speech recognition. But also, this phrase was in there that the acceleration of progress will depend in part on the availability of high-grade public data. In other words, common corpora. Now, even though they said that should happen, and people talked about it throughout the program, nothing really came out of it as as we will see. But the recommendation of the study was to fund for ARPA to fund a 5-year speech understanding research program, the so-called SIR program, and which ARPA did. And the participants included BBN, CMU, SDC, and SRI. And the task was to do continuous speech recognition of a 1,000 word vocabulary. Now, at that time, that was a very ambitious task. And the methods used were largely knowledge based methods. BBN, CMU, everybody, SDC, SRI, everybody used knowledge based methods, except for one particular effort by Jim Baker, who was doing his PhD thesis at CMU. He did it on what was going to be called eventually HMMs, but not at the time. However, and this was important, the advantages of that approach were totally lost on most people, including me and Raj Reddy, who was the PI of the effort at CMU, as we shall see. And the end of the program was only the very simplest tasks, a very small branching ratio of about 10, could be done in a reasonable amount of time. So when the new director Heilmeyer in 1976 at ARPA, who was basically a components person, he said, well, if you cannot do a really heavy task put it on a chip, do it in real time, it was not worth doing. So he stopped all work in this area. And as a result, the term speech understanding became what I would call a dirty word at ARPA. Now, at around that time in the 70s, Fred Jenilek and his group at IBM were working on statistical modeling methods, and the ones who established an information theoretic approach. And now the terms that we use today, like decoder and perplexity, were really done by them. And even though they had not used the word HMM at the time, they eventually settled on n-gram language model for words in any case, and an HMM acoustic model for phones eventually. Now, hidden Markov models, these were called initially probabilistic functions of a Markov chain. The theory was done at IDA in Princeton, New Jersey, with Baum and his colleagues in the late 60s. And as I said, IBM worked in similar models in the 70s. And in those years, these models were used at IDA and IBM, plus Jim Baker, who had interned at IDA. An important year or a day actually happened in 7 October 1980, a workshop held by IDA on hidden Markov models. There were about 40 invitees from AT&T, BBN, CMU, IBM, a number of other organizations from the US. At that workshop, IDA distributed this little book. We called it the Blue Book. And the title was Hidden Markov Models for Speech. Now, this was the very first time that these models became known as hidden Markov models. It certainly is a lot easier term to talk about than probabilistic functions of a Markov chain. This book was edited by Ferguson, and the chapters were authored by people from IDA. Now, that book had essentially all the basic formulations of hidden Markov models, including the EM algorithm, etc. And those formed the basis for the tutorial review papers by Rabiner and Zhuang, later on. Unfortunately, that book, IDA decided not to publish it, which is a shame because it's a great small little book if you can get a copy of it. In 1981, the following year, there was a conference held, a summer conference on applied mathematical problems, the so-called SCAMP conferences, and HMMs were featured in great detail. I attended that workshop, as did Rabiner from AT&T and others. And the work on HMMs had started already in earnest at AT&T, and we followed the suit the year after. Now, a couple of years later, DARPA now decided it wants to establish a program in strategic computing. And as part of that program, speech recognition was one of the components of that program. And the result of the competition was that CMU won the main contract using a knowledge-based approach led by Raj Reddy. And here the reasoning was a bit different than before. It was not so much production and perception. The reasoning came out as a result of a study that was done by Ron Cole, who was a psychologist at CMU. He invited Victor Zhu from MIT as an expert spectrogram reader. In fact, as people know, Victor Zhu was probably the world's best spectrogram reader. And the idea was, the proposal was, they asked Victor what he was doing as he was reading those spectrograms. And they decided was the basis of the proposal, to use the expert knowledge that Victor Zhu had imparted to them and build the speech recognition systems. At the time, as most of the speech community, except for those who had started to work on HMMs, they basically had the idea, and it was a fairly common phrase, that statistical approaches were incapable of modeling fine phonetic distinctions. So when we proposed at the time HMMs, we did not win, but a few small contracts were given to others, and the objective was for us, the different other contractors, to help CMU. But since HMMs really were not compatible with that knowledge-based approach, we decided to go ahead and build the complete system using HMMs on our own. And in February of '86, the very first evaluation, it showed a hint of the power of HMMs. But since there was no common evaluation, no common corpus, no firm conclusions could be made. Now, Alan Sears, who was the program manager, established semi-annual speech recognition workshops, and the first one was in '86, and they had published proceedings once each year. Now, during 1986, DARPA had site visits to the different contractors, And during the site visit to BBN, we decided to give a demonstration of our system. And those in attendance were Alan Sears, DARPA program manager, David Pallet, who was in charge of evaluations at NIST, and Ned Newberg from DoD. Now, the system, we called it Biblos after the old Phoenician town where the first phonetic writing was found. And since Byblos is now in Lebanon, I was familiar with that and with the history. I thought that Byblos would be an appropriate name for the system to emphasize the fact that statistical methods could, in fact, perform fine phonetic distinctions. And in order to show that, we built a demo. And the demo started left to right, doing the recognition of the sentence slowly. But at each point, the system would show a list of the competing hypotheses and so on and so forth until it was finished. And then the high scoring sentence would be shown, would be recognized. In this case, show the ships that were in home port on April 12th. And here was the number of hypotheses as a function of time. And here you would, if you would notice, you probably cannot see this, it took over 150 seconds, 2.5 minutes basically, to do the recognition. But that was perfect because you were able to actually watch it going on, watching the recognition, watching the phonetic distinctions being made as a function of time. This was really impressed the audience. In particular, it impressed Ned Newberg, who was, by the way, he was a speech scientist, like many of us, who was trained saying, okay, knowledge-based methods is the way to go. But after the demo, he said to me, this was the first time I could say that if you poured money into speech recognition research, it would be well worth it. And Ned Newberg had a lot of influence in the government. During that same year, 1986, there was a lot of planning going on for common evaluations that were insisted upon by Alan Sears, the program manager, and those visits were coordinated by NIST and uh, the collection of common corpora and the test procedures, the choice of training, test, what's the metric, and everybody was consulted on that. So it was decided to build two common corpora. One, TIMIT, which is still being used today, and it was recorded at Texas Instruments and is organized by TI, MIT, SRI, and NIST. It used to be called the National Bureau of Standards, and now, of course, we know it as NIST. It was 10 phonetically rich sentences read by 630 speakers, intended mainly for acoustic phonetic research. At the same time, DARPA insisted on a task domain speech recognition database. And this was for testing speech recognition systems. It was designed by NIST and other contractors, recorded at TI, and it was called the Resource Management Corpus of more than 1,000 sentences by many speakers that were recording for speaker-dependent and speaker-independent work. And that corpus continued to be used for a number of additional years. As a metric, the group decided that only, well, I should say NIST decided that percent words correct was required, but there would be no criterion for word beginnings or ending times, and reporting substitutions, deletions, and insertions was optional at the time. So the first common evaluation was in March 1987. At that time, only two teams participated, CMU and BBN, CMU using knowledge base, BBN using HMM, and it was competed using resource management. Now, there are other groups like MIT Lincoln Lab working on HMM as well, but they did not participate in the evaluation. Now, that evaluation showed a clear cut, better performance for HMMs. And the system had the advantages we know now. There's automatically trainable, does not require expert knowledge, only annotated data, much simpler to build, and the techniques that you developed are easily transferable to others. Also, what that workshop established, that evaluation, that the claim that statistical methods cannot model phonetic direct distinctions was no longer viable. But the people still believed, well, knowledge based methods must be good for something. Maybe perhaps they were better at locating word boundaries. So another test was held in 1987 where word boundaries in the test data were hand labeled actually by humans. And the systems were evaluated based on how well they matched the human experts in finding those word boundaries. And here again, HMM system was better at locating word boundaries. The upshot of all this was that by early 1988, CMU had abandoned all work in knowledge-based methods and had shifted all the work to HMMs. And the final metric that was decided upon by the community was what you are using today, the number of word error rate as the substitution, deletion, and insertion divided by the number of words in the reference. Now, the focus on error rate instead of accuracy was intentional because it was thought of as the cost of making these errors. That is, if you had to correct these errors, that would be the cost. So if you cut the error rate in half, your cost gets cut in half, and that's why we now talk about reduction in error rate. What percentage reduction in error rate? Following that program, other DARPA programs followed. There was a spoken language systems program, other NLP programs, neural nets, and in 1989, Charles Wayne, who took over as program manager at DARPA from Alan Sears, he also emphasized the use of common evaluations and had annual published proceedings. The first conference and proceeding. Oh, and by the way, he combined speech people and natural language people, and there were a lot of tutorial papers about fields to introduce the communities to each other. There was about 120 people from 17 organizations, including IBM and AT&T, who were not funded by DARPA at the time. Then followed 1990, the Air Travel Information System task. In 1991, there was attendance from Europe, and Charles Wayne decided to fund the formation of the Linguistic Data Consortium, which, by the way, was planned for by the community. And that consortium was formalized in 1992, and Mark Lieberman will tell us all about it in his talk about LDC. In September 1992, the very last resource management evaluation took place, and this time there was participation by Cambridge University and LIMSI from France, even though they were not funded by DARPA at the time. And of course, other corpora and evaluations followed with greater participation. What was the result of all this? Basically, establish the success of metrics-based evaluations, common corpora, and automatically trainable systems. Now, it doesn't mean that you have to have a automatically trainable system. It's just that if you do, the acceleration in the development of the technology is much higher. That acceleration also extended to advance when there were advances in computing speed and storage, And I would say, because of advances in both computing speed and storage and search strategies, by 1993, BBN gave the very first demonstration of a 20,000 word continuous speech recognition on an off the shelf computer at a DARPA meeting at MIT. And that paradigm, that benchmarking paradigm, spread to other fields within and outside DARPA, and it continues till today. Now, defining word error rate was straightforward, relatively speaking, was quite easy. But other metrics eventually had to be developed for other more challenging tasks: machine translation, summarization, other NLP tasks. So the task is still continues to be challenging. Finally, I would like to make a plea when people create new corpora. For every annotated corpus, please measure the inter-annotator agreement on a small sample of the data and publish the information along with the corpus. Now, that measurement does not have to be on a large amount of data. It really can be small because the accuracy is not that important. You just want to get a sense of what it is. Why is that important? Because the inter-annotator agreement really effectively places an upper limit on the accuracy of the models and the algorithms that you have. Basically, the inter-annotator agreement is a gate. It performs a gate on what can be done, what can be accomplished with the technology. We often get questions from our funding agencies. Why is it that your performance on one language is much worse or better than another? And very often the reason can be that it has nothing to do with the difficulty of the language, but rather the difficulty of annotating the data in that language, because perhaps for lack of guidelines, especially when the people are speaking in dialect. We did an experiment under Babel where we clearly showed the importance of annotator agreement uh, as it relates to accuracy. And finally, the original assumption around 1970 that we needed more than acoustic information to perform good speech recognition was basically correct. But what was thought of as speech knowledge was largely illusory because, at least with respect to its use in speech recognition, it turned out that really all we needed was a good statistical language model to capture this higher level information for the purposes of speech recognition alone, of course. The second thing was regarding the original dream of ARPA of computer researchers communicating with their machines via voice. That did not materialize. We don't daily, on a daily basis, use voice to communicate with our computers. However, all of us and people all over the world now are using apps like Siri and Alexa to access information and accomplish simple tasks via voice. But how to capture and use sophisticated higher level information like semantics continues to represent our holy grail. Thank you.